Okay, so last time we saw two basic ingredients that enter in the partition functions. One was the theta functions, so genus G on sigma G. We had the theta functions. So it is. I will from now on I will just write it as Z. Okay, but it's understood that this Z means really omega I, some base point P naught to Z. Huh? So there are G complex numbers. Instead of writing all the time, it's understood that this Z is the able map of the point in the Riemann surface to CG. Huh? That's a shorthand notation. So Z would mean when it's inside the theta argument, then it would mean that. Theta of Z, tau. So this we have seen already. And then the very important thing, which is the prime form, ZW. So these were the two basic ingredients we saw. And the properties of this was, both of them were, this was a minus half differential in Z, minus half differential in Z and W, both. Okay, that was the transformation properties of this. Under the coordinate transformation, that's how it transforms.
In the prime form, Z is actually Z.
Yeah, correct.
Okay.
Yeah. Right. So yeah, maybe I should not. Maybe this is going to be confusing. Okay. Yeah. Okay. Both of them are quasi-periodic. So let me see. A very important property of this one is that it has the only zero as a function of Z or as a function of W. The only zero is at Z equal to W. That is why it is so important, because that's what we need for the propagators. Okay, theta is, so the way, maybe I should write it down somewhere so that I don't erase it. There are these monodromy properties. Let's see. Right, the monodromy properties are, so around the A cycle, so what I mean by monodromy property, you move the point Z around the A cycle or around the B cycle, AI cycle or BI cycle, because there are G such cycles, then they don't come back to themselves, they are multiplied by some factors. Around the A cycle, they are invariant. Around AI cycles, they are invariant, meaning they come back without any extra factors. But around the B cycle, so if I move, say, the point Z around B cycle, so move point Z around BI cycle, ith cycle, then this goes to, so under the BI cycle, this picks up a phase which is e to the power of, let me just see, I think, yeah, e to the power of minus I pi tau I, so ith one, this ith one, and minus 2 pi I Zi. So what is Zi? Zi is this guy. So Zi is this. Okay.
In the prime form, you do not indicate that it depends on the tau.
Yeah, it is understood. Everything is, yeah, maybe I shouldn't, there's not even need to put tau there, because it's understood that it's all on a given Riemann surface. So as you change tau, it will be different. Yeah. Okay, and the E, so this times, of course, original theta. So what it means, Zi, is the ith argument. There are G of these guys, right? Ith argument, which appears there. And Ez picks up a phase, which is, again, e to the power of minus I pi tau I. And actually the same thing, minus 2 pi I. And now there are two objects, Z and W. So this will be Zi minus Wi. It's not surprising because EZW was, in the construction of EZW, we started with theta of Z minus W. So that's the reason why. Okay. I mean, I may have made some mistakes, but I mean, I'm not sure this sign, but I think it's more or less correct. It's all given in the Verlinde paper, Verlinde's paper, Verlinde Square's paper of. No. Yeah, this is the paper of Nuclear Physics 1987. 97. Sorry, 87. Yeah. And I don't know, the page is, B. Oh. I think I gave the reference before, 288, I think, and page 357. No, the problem is I have difficulty reading it. That's why. Yeah. Okay, so this is a very nice paper. Okay, so this is the monodromy properties. Now we'll need one more object, which is not very crucial because at the end they all cancel out. I mean, but nevertheless, at the intermediate step, there is a particular object which is denoted by sigma z. This has a property that this transforms under the coordinate transformation as a g by 2 differential. Okay, g by 2 differential, and the other property is that it has no zero or pole. So in that sense, it's like a trivial bundle. The divisor is trivial. So these are the two properties, and the transformation properties again around the A cycle it doesn't change, and around the B cycle. So if I move around the B cycle. BI cycle, it is, it's e to the power of minus I pi g minus 1 tau I minus 2 pi I delta I plus 2 pi I. Okay. Delta I again is the ith component of the delta, right? The Riemann theta constant. Times, of course, sigma. I also forgot to write there. I forgot to write there also. This times the EZW. So these are the important properties. Sigma, explicit form of sigma I will not give the explicit form of sigma, but what I will do is I will give you a ratio of sigmas. And that is all that is needed, because in all the correlation functions, it will always appear as ratios. So sigma of z divided by sigma of w is the same as E of z minus sum pi plus delta divided by E of w minus sum pi. This I is not the same as that. These are points. Each pi is a point on the Riemann surface. And this I goes from 1 to g. Plus delta. And then product of E z w minus pi, w pi divided by E z pi. Pi are arbitrary points. Okay. Now this looks a bit strange because here there is no information about the p, but on this side we have information about the p. But you can show that actually this is independent of pi. Right hand side is independent of pi. I is equal to 1 to g. Okay. The way to see this is that if you look at, let's take P1. As P1 under the coordinate transformation, this is a minus half differential, that's a minus half differential. So the ratio is like zero differential, right? And then you also see that it has no poles or zero. For example, let's look at, say, P1 goes to Z. There is a pole here, but then by Riemann vanishing theorem, this also, if P1 goes to Z, the remaining part is a positive divisor, so that also vanishes. So this way you see that there is no pole anywhere. And it's a trivial bundle as a function of pi, so it must be constant. So that's the kind of argument. Okay. So now I think these are the basic ingredients. Huh?
First, you write is equal to E over Z, it shouldn't be theta eventually?
No, sorry. What am I saying? This is, no. Yeah, you're right. I mean, wait a minute, I think. Theta, correct, theta, yeah. This is theta. Sorry, this is theta. Yeah. Okay. All right. So now using this, we can immediately, this information, we can immediately write down, say, the fermionic correlation function, psi bar z, psi w. Right? That is the Szego kernel. This one, whatever it is, the answer, whatever it is, we can see that it must be dimension half in z, dimension half in w, right? Because these are half differentials. And the answer is simply EZW. And then, since it's a half differential, there are spin structures. So there are different spin structures. And the spin structure information comes here, Z minus W. Okay. That's the thing. Now you want to also normalize it so that the coefficient of the first order pole is as 1. And that you can easily do by dividing by theta alpha of 0. Okay. So I forgot to mention that the E has a first order 0, and one has normalized the E in such a way that near Z goes to W, this E is simply Z minus W with coefficient 1. Okay. So one has normalized it in that way. Okay, so this is the famous Szego kernel. Okay. So in principle, if you have this is of course in the even spin structure. Huh? This is alpha. We are taking alpha to be so in the even spin structure. In the odd spin structure, they have 0 modes, so they will just give the 0 modes. Okay. Yeah. In general, if I have take say products, say Zi, psi bar Zi, psi Wj, Wi, let's say, and product I from 1 to something, k, let's say, then I can just use the Wick's theorem, because after all, these are free fields. So you'll get you can just, each pair-wise, you get these Szego kernels, right? And then there'll be all possible combinations. So that's one way of doing it. But then we know that there is bosonization that we have seen probably in the CFT, in the conformal field theory, we have seen the bosonization, and it will turn out that it is much more convenient for us to use a bosonized language. Particularly since we'll need the spin fields. Okay. So for the spin fields, it is easier to work with the bosonic description. So what today I will do is just to go through briefly, I'll just summarize the papers the results of Verlinde, this paper, which basically establishes the bosonization, uses the bosonization language to compute the higher genus correlators. Okay. Up to the tree level and the one loop, it's already well known. Okay. What they have done is for the higher genus. Okay, so let me just remind you what is the... So the idea is that if I take one complex fermion, which means 2 real fermions, then that is equivalent to 1 boson. So psi bar psi, and what we can say that psi is, for example, e to the I phi, and psi bar is e to the minus I phi, okay, where phi is one scalar. Compact scalar. So that is the case for the fermion, but you can actually do this for arbitrary anti-commuting variables. For example, in our in string theory, we have BC Go system are anti-commuting, but they are not half differentials. B is has dimension 2 and C has dimension -1, right? And in general, I mean, so any anti-commuting system which is some lambda differential, so let's call it B and C, this is some lambda differential. Okay, so for the usual fermion, lambda is half. For the B ghost, lambda is 2. So quadratic differential. And C will be 1 minus lambda differential. That is clear that it must be something like this, because after all, in the action, we have something like, let's say, B d bar C, right? That is a typical term in the action, right? Now, if this is lambda differential, that means if I put down the both holomorphic and anti-holomorphic weights, it will be lambda comma 0. It has no anti-holomorphic weight, right? C will have 1 minus lambda, 0. And d bar gives a transformation property as 0, comma 1. So altogether, when you add that up, it becomes 1, comma 1, and that you can integrate over the worldsheet, right? So that's why the pairing is always between lambda and 1 minus lambda. Okay. Okay. So the question is, how does one? So what is the? Maybe I should. No, anyway, I think this I cannot erase it. The stress tensor T for the BC system is in the conventions that we are using is minus lambda B dz C. So this is TZZ, I mean the holomorphic part, plus 1 minus lambda dzB C. Okay, that is the stress tensor. And one can compute, of course, the central charge using this. By the way, this combination precisely is such that it doesn't matter. I mean, whether you use covariant derivative, which you need the connections here, whether you the connection term cancels this combination, so you can just replace it by ordinary Z. Okay. And one can indeed check that the correlate. I mean, if I look at the OPE BC is 1 over Z minus W, that indeed it correctly reproduces the dimensions of B and C. And yeah. And its central charge is, what is the central charge? 1 plus, is it correct? Let me see. Q square, where Q is 2 lambda minus 1. Okay. I think that should be correct, probably. So, maybe it's a minus 1 somewhere, 3Q square. Minus 1. 1 minus 3Q square. 1 minus 3Q square. Correct. Exactly. So so then this will produce the correct thing. So for example, if lambda is half, then this cancels and you just get C equal to 1. That is for one complex fermion, central charge is 1. And for lambda equal to 2, you get the minus 26. Okay, so this is the stress tensor. Now you can actually bosonize this. Again, write B equal to e to the I phi and C equal to e to the minus I phi. But you see that it cannot be as simple as in the case of fermion, because a usual scalar, one scalar will have central charge 1, right? But this is clearly not, in general, it's not central charge equal to 1, right? So only special cases when lambda equal to half, in which case it is bosonized to just a free scalar, right? ordinary scalar. But in the generic case, it's not the situation. And in fact, what happens is that this phi couples to a background charge. And in fact, the action for this boson, the scalar, is d2z, the usual dz bar phi, dz phi. That's the usual thing. But there's an extra piece, which again, I'm not sure about my normalizations, etc. But it's something like this. So it couples to the curvature, the worldsheet curvature, okay, with the coefficient which is proportional to q. And one can indeed check that if you write down the stress tensor now for this scalar, for this, just very with respect to the metric. So you can write down the stress tensor, and it happens to be t equal to minus half dz phi, dz phi, dz bar phi, dz phi, plus 1/4 I, no, minus 1/2, sorry. I mean, these numbers, I'm not 100% sure. You should check it. IQ dz square phi. Okay. There's an I there, yeah, for that. Yeah. Where we are taking the phi correlator, phi z, phi w. Correlator is minus log z minus w. Okay. So with this stress tensor, it's easy to verify that if you look at tw and look at the coefficient of z minus w to the 4, which gives you c by 2, that c is the same as that c. Okay. That one can check. And furthermore, you can also see that since there is a modification, so if I write down some e to the iq phi, vertex operator, its dimension will not be simply q squared by 2, right? Because there's extra piece. I mean, that will give you q squared by 2. But there's an additional piece which will give you something proportional to q times capital Q, right? And one can check that the dimension of this dim of this is 1/2 q times q plus capital Q. Okay. So, for example, if I take q equal to, for the BC system, the ghost system, lambda is equal to 2, so q is 3 for the BC system. So if I take q equal to 3, then you get here, and small q is equal to 1. So I mean, this will imply that e to the I phi, if I take the small q equal to 1, has dimension equal to 1 plus 3 divided by 2, so it's 2, right? This is for q equal to 3. And on the other hand, e to the minus I phi will have dimension 1 minus 2, so it becomes minus 1. Okay? So that's exactly the dimensions of BC system. So this is the way one bosonizes it. I mean, such kind of systems have already been studied in the context of minimal models, okay? Where minimal models, the Coulomb gas representation of minimal models, C less than 1 models, where you can realize the minimal model in terms of one scalar field, but scalar field with some background charge, something like this. And that then that can, so that it reproduces the correct central charge, and then one can actually, describe all the correlation functions, structure constants, everything in terms of the scalar field for the minimal model. This is all this works of Dotsenko and Fatiev and all these people. They have done a lot of work in that. Okay. But okay, this is now in the context of, it's not C less than 1, actually, it's a different system. Okay, so right. Okay. Now, of course, this system has zero modes. The number of B0 modes, so there are a number of B0 modes is equal to, in fact, 3G minus 3, and number of C0 modes is 0, right? These are the 0 modes. There's a general theorem due to Riemann and Roch theorem. Which gives a number of 0 modes for any line bundle. Okay, I mean not some differences actually. It gives more precisely differences of number of 0 modes for line bundles. So let's say, suppose I have a line bundle L, and the kind of conjugate line bundle, which is the canonical bundle times L inverse. This is for the same reason, because I mean if I take the product of these two guys with a d bar derivative. I mean, think of this as a B field, and B is living here and C is living here, then it's exactly that. So you have, if I look at B d bar C, when you take the product of these two guys, the L inverse, degree of L inverse L cancels out, because degree is additive, right? The degree will be additive. So degree of L will cancel out, and you're left with a canonical bundle, which is a 1 differential. So B times C transforms as a 1 differential, 1, 0, and d bar gives you the 0, 1, so you can integrate. So that's exactly that same discussion here. What it gives, Riemann-Roch theorem, is actually the index of the d bar operator. Okay, index of the d bar operator acting on, say, line bundle L, this system. So it gives you the number of 0 modes of this line bundle minus the number of 0 modes of that. Okay, so the number of 0 modes of L minus the number of 0 modes of KL inverse. That's equal to the degree, is completely given in terms of the degree of L minus G minus 1 for genus G. Okay. This is a very important theorem, I mean, Riemann-Roch theorem. Okay, so for example, so if I now look at this specializer case. So we have the degree of L. So the degree of L, so let's take various cases. Suppose lambda is 1, let's say. I mean, in this case, lambda is equal to 2. If lambda is 1, this formula is saying that, so the number of 0 modes of lambda differential, of 1 differential, minus the number of 0 modes of 0 differential, because this lambda equal to 1 means this is K itself, right? This is the canonical bundle. And here you have a K inverse, so it's a trivial bundle. Function. These are functions. Okay. That's equal to the degree of L, which is 2G minus 2, minus G minus 1, which is the same as G minus 1. Okay?
So G is greater or equal to 2?
G is greater than or equal to 2, yeah. Yeah. Right. I mean, I think this formula is generally true, except that for G less than 2, maybe I'll just come back to that point. Yeah. No, this formula is generally true. It's generally true, yeah. Yeah. Yeah, exactly. So it will just go, so this is general formula for G. But you see, this does not give you separately the 0 modes of this and that. It only gives you the difference. So you need some additional information to fix each of the 0 modes. So for example, here, now this is the information we have from the Riemann-Roch theorem. But we know that the number of scalars, number of functions, the holomorphic functions is exactly 1. It's just a constant function. So we know this is 1. Okay? So therefore, that better be G. Which also we know, because there are G holomorphic differentials, abelian differentials, right? So, okay. Now, let's take G equal to 2. So this is fine. Lambda equal to 2. I think I can erase this part now. Yeah, if I take lambda equal to 2, then so we get here the So we have, let's say, k square. Huh? So this is the number of zero modes of quadratic differentials, right? Which means b, for example. This will be like what we call b, minus the number of kappa times, k times k. So this is k inverse. So this is the c. Okay. That's equal to, we are saying, so it's 4g minus 4 minus g minus 1, which is equal to 3g minus 3. Okay? So this gives you the difference between these two, right? However, in this particular case, we can get more information because, you see, the k itself is a divisor, 2g minus 2 divisor, right? Degree of k is 2g minus 2. So degree of k inverse is minus 2g minus 2. Okay. Now, remember what is the degree? Degree is, if I write down some section of this line bundle, then it just counts a number of zeros, the zeros minus the number of poles. The positions of the zeros and positions of poles. Now, if the degree, so not this one, so this is that. If the degree itself is negative, there is no way, every section must have some pole. Because zeros come with a positive sign, poles come with a negative sign. So immediately you see that if the degree is negative, there is no way it can have a zero mode. No way it can have a holomorphic section. Okay? So we have that for G. This is where I'm using G greater than 1. Huh? Because otherwise, if, for example, if G equal to 1, this vanishes. So I cannot say anything about it, right? A priori, I cannot say anything about it. We need more information. Or G equal to 0, actually this becomes positive, right? So that is where I'm using. So for G greater than 1, this is always true that C has no zero mode because it has negative degree, so it's not possible. Okay. So therefore, this gives you a complete information. So this has no zero mode. This must be 0. The number must be 0. So therefore, it tells you the number of B zero modes is 3G minus 3. Okay. Like that. So one can, let's say, what about we have other situations. By the way, this gives you no information for half differential. Because you see, if I look at, if L is k to the half, then the left-hand side is 0, and right-hand side is also 0. So no information. Okay. But let's take k to the 3 half. Okay. This is the case for the super ghost, the beta-gamma system, right? Beta has dimension 3 half. Beta has dimension 3 half, and gamma has dimension minus half. So that's exactly that system, beta-gamma. Of course, this is commuting, but it doesn't matter. Riemann-Roch theorem doesn't care about whether it's commuting or anti-commuting. At the level of correlation function, it will make a huge difference. But at the level of counting, the zero modes, it doesn't. It's the same thing. So you have k to the 3 half. So then I will get here, the number of beta zero mode minus number of gamma zero modes is equal to, so now you get 3G minus 3, because 3 half times the canonical bundle, so that's the degree is that, 3 minus G minus 1, and that's 2G minus 2. So there are 2G minus 2 zero modes, right? And once again, you see the degree of beta, this is 3 half, so it's degree of this guy, degree of this is 3G minus 3, and degree of that is minus G minus 1. So for G greater than 1, this is negative. So gamma has no zero mode, but beta has. So beta has precisely that many zero modes, 2G minus 2. Yeah. This situation is opposite for the G equal to 0 and G equal to 1. So for G equal to 0, you see that this is G equal to 0, this has negative degree. So beta has no zero mode. Okay, gamma, and so therefore this tells me that the number of zero modes of gamma is actually 2. Okay, that's exactly what we remember, that in the NSR formulation on the sphere, the total picture must be minus 2, right? That is the reason for that. On the other hand, this Yeah. For g equal to 1, it's a bit special because this degree, both the degrees are 0, right? And in fact, in general, there will be no 0 mode. I mean, it depends on which spin structure, because this is half differential, so you also have to specify which spin structure you're talking about. It will turn out that for the odd spin structure, there will be exactly 1 0 mode for each. But for even spin structure, there will be no 0 mode, right? Because g equal to 1, this is right-hand side is 0. So whatever the number of 0 modes must be equal. And then the 0 modes depend on which spin structure you're talking about. Okay.
So odd spin structure means Ramon sector.
Odd spin structure will be, I mean, not just Ramon, but also periodic boundary condition in the time direction. Yeah. Yeah. Correct. Yeah. So yeah, that's.
Was 1/2 or 2 of 2z
Yeah.
times 2g minus 1.
Yeah. Correct. So it's I mean, that odd spin structure for the torus appears in this way, in the sector, where here it's periodic and there also is periodic. Huh? That's periodic. That's why there is a fermion 0 mode, right? I mean. Okay. So the upshot is that if I want to compute the correlation functions of BC, there are 3g minus 3 0 modes for the B. So in order to have anything non-zero correlation function, you better be able to soak, you should be able to soak the 3g minus 3 0 mode, right? So therefore, what we have is that the correlation function that will be interested in is, I mean, which will be relevant in general, will be some number of b, zi, I going from 1 to, let's say, I goes from 1 to something, n, and product of c, wi, wj, let's say, j going from 1 to some m, let's say. Then we are saying that n minus m must be equal to 3g minus 3 for it to make sense, for it to give you something non-zero. Otherwise, it will be 0. So this must be true, otherwise it is 0. Otherwise this correlator is 0. How does one see that in the bosonization picture? In bosonized language, we said B is replaced by e to the I phi. This is replaced by e to the minus I phi. So what we are saying is the total charge of the phi is not 0, right? Actually, it's 3g minus 3. Okay. But that's exactly the background charge. I erased that. Yeah, this somewhere I wrote down. Yeah, this background charge. So when you have the path integral, you have this action in the exponential of this action. So this gives you the Euler characteristic. Okay, when you integrate it. So take the 0 mode of the phi. I mean the constant mode of the phi. Then you can take that out. This just gives you the Euler characteristic. So Q times the Euler characteristic. Okay. So that gives you additional, I mean, some charges coming from the action itself, which is called, that's why it's called background charge. Huh? That background charge will exactly cancel this excess charge here. Okay? That's how you see the charge, I mean, this statement there in that language. Okay, so now let me just state the result of Verlinde. So Verlinde have given this formula for this correlator, and they did, a very beautiful work. I mean, they actually went through the bosonization and the singularity structure you immediately see, right? When Z approaches W, you should have a first order pole. When two Zs approach each other, it should have a first order 0, right? So these things you immediately see. But the details include also the solitonic sectors, the instanton sectors of the scalar field, right? Because the scalar is compact, so it can have windings along the different cycles. So they go through this entire calculation, and I will just state the result. So the result is, so this correlator, So let's B, Zi, C, W, J. This is, say, M. This is N. N minus M is 3G minus 3. And that's given by the product forms. So as we expect, there should be E, Zi, Zj, right? Because when two Z's approach, they should have a 0. Similarly, E, W, I, Wj. And then, so this product is I less than J. Maybe put a different index, K, L. K less than L. I mean, each pair will just give one term, right? And then when this approaches that, you should have a pole. So there should be E, Zi, Wj. So product over I and J in the appropriate range. Now, this part was immediately obvious, right? The instanton part gives you a theta function in the numerator. I mean, so this is whole thing is times theta function of, I put here alpha, okay? Because this is the general statement. I mean, it need not be just for, okay, in this particular, so this is not 3G minus 3. In general, it is Q times G minus 1, more generally. Q is 2 lambda minus 1. So this is more generally that. So it could be anything. For example, I can take just lambda half differential, for example. So this formula is a general formula. So it could also be some half differentials, in which case there will be spin structures. Okay? But if it is not a half differential, if it is an integer differential, then there will be no spin structure. So it's understood this is only for the half differentials. Otherwise, there is no alpha here. So then this will be sum over xi, zi, minus sum over wj, minus q times delta. Okay. That is the, now there is some more terms, which let me just come back to that for a moment. Again, you see that this kind of an argument, there are, how many of them are there? There are n of these guys, and there are m of these guys, right? And this one, delta is a divisor of degree g minus 1, right? Is a half differential delta. So this is q times g minus 1, the degree. So you see that this exactly, so n minus m minus q g minus 1, so that is 0. Okay? So whatever appears in the theta functions inside, it should have 0 degree, right? Otherwise, the base point, it will depend explicitly on the base points. But that should not, because base point is totally unphysical. I mean, you just choose any base point, right? So that is one check immediately. That make sure that everything, otherwise one has missed something. No? Make sure the total degree is 0. Okay? Degree of this total divide is 0. Second thing is that, now if we know that this is a certain dimension, that is a certain dimension. And prime form, we know the dimensions. So for example, if I look at, say, Z1, okay? Z1 will appear how many times? So there's every time there is a Z1 appearing here, it will contribute a minus half, the dimension. Because E has a dimension minus half. So how many times it will appear? This is I less than J. So all these J which are different from I. Let's take Z1. Okay? So take Z1. Then how many times it will appear here? N minus 1 times, right? So you will get a minus half times N minus 1 coming from here. Okay. Here you will find this is for all W's, Z1. This is for, if I fix Z1 here, then all the W's are appearing here. And that is how many? The M number of them. But that is the denominator, so you'll get here plus half M. Right? That is the, that is as far as this dimension is concerned. But that's not the dimension. The dimension here is, what did we say? It is, it's Q, no, what was the dimension for the B in general formula? I'm getting confused here. It's Q times the, Q times? It was Q, correct. Q 2 lambda. Correct. But I mean, directly in terms of the bundles, we can say, right? B is a quadratic, B is a Q, quadratic differential. So it will be simply lambda itself, right? Lambda times lambda dimension. Yeah. So this should be the dimension here, but what we are computing is that. Okay. What I'm saying is that you'll see that this is not. There's a big mismatch between this number, and what you should expect a dimension. Okay. That is where the sigma, this strange object that I wrote down before, enters, and you can just write down just by counting the dimension, you can write down, and the answer is sigma of Zi divided by sigma of Wj to the power of Q. Okay. So this is the product over all I, product over all, say, J. This is what appears here. Okay. So this has a G by 2. This is a G by 2 differential. So this will give me another, for say, if I look at a Z1, it will give me Q times G by 2. Okay. Then I think if you add up all of that, you should find, precisely the correct dimension. Okay. Yeah, I mean, you have to use this formula here, n minus m, substitute that, and then QG term should cancel, you see, because there should be no G dependence in the thing. That is why you can immediately see from the, this one will have a G dependence. From here you get Q by 2 minus Q by 2G, just coming from these two terms, right? And then there will be a plus half here. And that minus QG by 2 should cancel from there. So that you can see from there. Okay. So this is the general feature. I mean, for all these anti-commuting objects, it's very easy to write on the correlation function, even if we don't even have to go through all the soliton calculations. That just by look at the dimensions, so you know how many sigmas should be there, and furthermore, this monodromy. You see, this monodromy transformations. Every time you make a monodromy transformation here, let me say take move Z1 around the B cycle. These things will pick up phase, right? Similarly, these things will pick up some phase, but it should be such that the phases cancel. Okay. If there is no spin structure, if there is spin structure, it should be an appropriate phase corresponding to the spin structure. Okay. So that completely fixes this. There's no more freedom there. Okay. Now, see, 11:30. The super ghost system, maybe I can just start talking about super ghost system. Is there any question before I move on to that? Is there any question here?
The normalization is completely fixed.
No, overall normalization, no. Overall normalization is not.
The zeros of colliding B's is okay. The zeros of colliding C is okay. The poles of B and C is okay. But the theta's and the C.
So I should mention here, when I say correlation function, I mean this is the full result of the path integral. Okay. So in other words, this is really what I mean by this is dB, dC, and e to the minus s bc. The result of that path integral is that. And there are some factors which I should write down. So the bosonization, so there is this factor times divided by, once you write it in terms of bosonic language, you have the partition function for the one scalar, right? So that partition function will be some 1 over Z1 to the half. Z1 is the partition function for one scalar, okay? So, meaning the determinant of one scalar. Scalar determinant. So when you have one scalar, you have a square root of determinant of scalars, right? So there is this factor, but that is not Z and W dependent. Yeah, but there is tau dependencies there, of course, right? So that is there. So yeah, I should write down. In fact, in his formula, there is also, in Berlinde's formula, there is the Z1 also floating around. Yeah, I think it's there. Chiral determinants. It should be there because, I mean, you're just doing the scalar determinant, so it should be there. I cannot find it here. It should be somewhere. Yeah. Anyway, how can I not find it? Strange. Okay. So remember, the way this calculation is done is go to the bosonic language. This will be replaced by e to the I phi. This will be replaced by e to the minus I phi. Take into account the background charge. Okay. So write down the scalar correlation functions, scalar Green's functions, and then you get that. This comes from the instanton contributions. Okay. You have to sum over that. Typically theta functions come from that, the instanton contributions. And then you have the non-zero mode determinant of the boson, which will be that object. Okay. So that is the way it works out. The incident contributions, because you see that, I mean, if I look at some Riemann surface like this, the phi is a compact scalar, right? Phi is a compact scalar. Yeah. So what they do is they take the full solitonic contributions and you can separate them into holomorphic part times the anti-holomorphic part. So this formula that I've written down is a chiral part, holomorphic part. Okay. So in fact, you see, before Berlinde, there was already a paper on bosonization, very beautiful paper by Alvarez-Gomez et al. Alvarez-Gomez, Moore, and Waffa. Okay. But they didn't do chiral bosonization. It was really taking the full left-right symmetric system, right? And then they gave a formula for that. But Berlinde's formula is very useful because in string theory we have, the holomorphic, and particularly when you look at, you say, even in the NSR, I mean, the type 2 theory, you have a separate spin structures on the left and separate spin structures on the right, right? So you need kind of chiral bosonization. Okay. That is what these people did. I mean, they. Yeah, instantons will give you something of this form, okay? But there will be also some anti-holomorphic sectors. Both sectors will be there because instanton sums will be both, depending on tau and tau bar. Yeah, you throw that out. Yeah. Right. But yeah, I mean, as I said, okay, whatever they did all this instanton calculations. But here we can just fix it by monodromy. Monodromy invariance, you fix it immediately. This particular theta functions. Anything else?
Where does the sigma over sigma come from?
Yeah. Right. I mean, it's that sigma term is very messy. Sigma term comes, I think, from this background charge. So there are this curvature term, and it's a very difficult analysis, that sigma term, because in fact that's the reason why one just gives a ratio of sigma z over sigma w. The full sigma is not easy to write down because it involves all sorts of conformal anomalies and everything. Okay, so that's why one, but the ratios are fine. But it's the origin of that is the background charge. That R term, the coupling to the square root of GR. Yeah. But at the end, as we said, I mean, only the ratios will appear when you look at the full partition function, not just one particular subsystem. Here you see it's not, the number of sigmas up and sigma down is not the same, right? But when you put together all the partition, all the components of the theory, then it will cancel. I mean, it will be the same number of sigmas up and down. Which has got to do with the fact that it's a critical string, right? So it should not depend, it should be conformally invariant. Okay, that's so when you put together everything, all the systems, then there will be no conformal scale dependence. Yeah. Huh? Yeah. Right. Yeah. Okay, so let me just start the discussion on the super ghost. Super ghost is again, there's a bosonization formula for the super ghost. This is already appearing in Friedan, Martinek, Schenker. This is a bit more complicated. So beta is dimension 3/2, and gamma is dimension -12. And the central charge, the total central charge of this system is 11. Okay, that is, that's why the superstring is critical string, right? So that's the dimension of this. Now the way you do the bosonization is there's one scalar field phi with some background charge, but there is also an anti-commuting 1-0 system. So one differential and a scalar, okay? And that is called eta-zeta system. Okay. That's the... So since beta is half differential, beta and gamma are half differentials, half integer, theta 3/2 and -12, they carry the information about the spin structure. So they are not neutral to the spin structures. Okay. So the formula was, the identification was, I think it's beta is deep psi, I think, e to the I phi. Or maybe I'm going the other way. Gamma is eta e to the minus I phi. Is that correct? Huh? Sorry, this is minus? I think. Huh? No, I also. Are you sure this is plus and that is minus? I don't know. Huh? I may be wrong. Huh? Well, the background charge is there, right? There will be background charge. Yeah. I can't find the formula. Yeah. Beta is deep psi minus phi. Correct. You're right. Yeah. E to the minus phi, and that is plus phi. Gamma is e to the plus phi, and so this system, the beta gamma system, eta psi system. This is the dimension 1-0. So its central charge will be central charge of this system will be -2, right? Because we have a general formula for the central charge for any anti-commuting system with different dimensions. That will be central charge -2. And the central charge of this the scalar, the field phi, should better give central charge +13, right? To get the total central charge 11. Yeah. And here, one writes down the scalar field, which has some background charge, so that the stress tensor of the scalar field is -12 d phi square -1/q d square phi. Note that there is no I there. Q -1 q -q -12q d square phi, where q is to lambda minus 1. So lambda is 3/2, so in this case, this is 3/2, so this is 2. Okay. Sorry?
You were saying that phi has to form a weight 13.
No, the central charge. Sorry, the central charge. Central charge is 13, yeah. Okay. Now this system is a real mess. I mean, they write down. In fact, I don't know how they were able to guess to get this kind of a complicated answer. But fortunately, for our purposes, we'll need only a much simpler situation. Okay. So again, so one can just check from here that the dimensions of these guys come out right. I don't have these formulas here. I think Q. I think the dimension of this object, if I write down e to the power of q phi, the dimensions of this object will be, this operator will be minus half q times q plus q. I'm not sure again. I mean, one should, check that. But we can just check it roughly what. So capital Q, let's just check that e to the minus phi. So q is minus 1. So minus 1, and this is 2. So 1, this is minus 1. So this is half, right? So this dimension gives you half. And deep psi is dimension 1. So this is correct. I think this formula is correct. And eta is dimension 1. Now, one important part of this thing is that, you see, in this Bosonization, we are kind of, psi never enters everywhere, anywhere. Psi enters only through the derivatives, right? There is no psi. In this dictionary, I mean, our original system was beta gamma, right? That was our original system. Now we are replacing that by eta, psi, and the phi system, okay? So in this dictionary, only the d psi appears, which means the zero mode of psi is not in the original Hilbert space of beta and gamma. The zero mode, right? Psi is, remember, is dimension 0. So there will be a constant mode for psi. So that is not there, right? So you must remove the zero mode of psi. Okay? And that is what happens. So what you should do is that every correlator, one way to do that is that whatever correlation function you write, whatever operators you have inserted, various operators you may have inserted in different points, you should also put somewhere psi, one psi. Or more generally, you should have, one psi you need anyway. I mean, in our situations, it will be just that, just one psi. We will not need more than that. Okay. So this will do what? It will just remove the zero mode, and then you can just do the remaining path integral, right? Where you have all the other non-zero modes are taken care of. The thing is that this will be independent of the, doesn't matter where you put. The reason is that whatever other operators you put here, okay, they will always involve at least one derivative of psi. So there is no way these guys can soak the zero mode, right? I mean, imagine that there are other operators also involved some psi. Then you have many possibilities, right? This could soak zero mode or that could soak zero mode. Then you cannot say whether it's much more complicated. So, but everything else involves a derivative. Okay, so the only way a zero mode can be soaked is that, and zero mode is a constant, so the position does not matter. Okay, that's one thing. Then the other issue is that in this description, for every vertex operator, you have different pictures. You have possibly different pictures. Ghost numbers, different ghost numbers. Okay. So, for example, we know, for example, let's say if I look at the standard vertex operator, e to the I p dot psi, so for any x psi, right? This is the left moving part of the operator. This is dimension 1. But then there will be another -1 picture, which will be like e to the minus phi, where phi is this phi, times psi. Okay. That's another version of that. Now one can compute the dimensions of that. This object should give, I mean, if these formulas are right, this should give a dimension 1/2. That has dimension 1/2, so it should be dimension 1. Okay. So how does one go from one picture to other picture? And that is done by something called PCO, picture changing operator. I mean, this is all discussed in detail in original paper of Friedan, Martinek, and Shankar. But I just remind you this. The PCO, this is a short form PCO, that is obtained by applying the QBRS on psi, on this psi. Okay. So that is the operator. It has many pieces. It has, for example, a piece. Remember that in the BRST operator, there will be something called, apart from the usual the bosonic part, the stress tensor, and so on, there will be also a term which will be gamma times the fermionic part of the stress tensor, gamma times TF. Now, gamma involves eta there, right? So that when you do the contour integral of the BRST current around that, it will precisely pick up a TF. Okay, so there will be a piece which will be like e to the phi TF. Okay, and plus other things. It's not the only story. There will be other things also, but this will be certainly there. And again, for our purposes in our calculations, it's only this one which will be crucial. Okay. So this is what is the most important point. But so how does one? I mean, sorry, any point? No. So to go, you can apply a PCO, apply this transformation, and you find if you apply this PCO on that, you find this operator. Okay. By the way, PCO has dimension 0, right? Because this is psi has dimension 0, and QBRS, you are just doing contour integral. That's not going to change the dimension. So this is dimension 0. Okay? And dimension 0 object you can put at a point, any point. Right? So when we say PCO acting on that, you basically put the PCO there at this point, right? And then you can show, it's not very difficult to show that you get this operator. Right? Okay. And how does one show that the result should be independent of which picture you use, right? And that is done by precisely this kind of a mechanism. So let's suppose I have an operator here in some picture. Let's say I put this operator. So this is in -1 picture. Okay. And something else here is in 0 picture, let's say. Now, how do I know? I mean, maybe I change this to -1 and that to 0. Will the answer be the same or not? Okay. The way you do it is that, you see, I can write this object as, so this 0 picture, this is 0 picture. I can write this as a PCO. So let me put here a PCO acting on a -1 picture operator. Okay, that I can do. Now this PCO, I can write it as a QBRST psi. Okay, then you move the QBRST. Okay, and you can act it there, and it becomes 0 picture. And if your BRST is a good BRST symmetry, which means that there are no boundary terms in the moduli space which contribute, etc., then this is perfectly valid, right? So this is if this was not true, then forget the boundary. Even the bulk term would be absent. Would be present, right? So this is the way one argues that the different pictures don't matter. The other thing you can ask is what happens. I mean, if let's suppose I have some PCO sitting somewhere. Okay. Now, will it depend on this position? Will the result depend on the position? Because, this is a dimension 0, so you should put it at a point. There's no sense of integrating it, right? You should put it at a point, but will it depend on that position? Again, the answer is no, because you can write this as QBRST acting on psi. You deform the contour. Okay. All the other operators are physical states, so they are annihilated by QBRST. Okay. So where it can hit there. So this will be converted into PCO. When it hits, here is a psi, the other psi, which was there to soak the zero mode of psi. Right? So this will hit there, and it will convert into PCO. But in that process, you have changed the position of PCO. Right? So you can see easily that this way that it doesn't matter where you put the PCO. Answer should be independent of that. Okay, is that clear? Yeah. Okay. Now, how much time I have now? 15 minutes. Huh? Okay, so let me just write the formula for the correlation function. So Verlinde et al. Have given a completely general formula, but I will just specialize it to the case that we are interested in. So they have given a general formula with the arbitrary number of xi's, and then some arbitrary number of etas, and exponential of qk phi of say tk. Okay, they're given this formula. But what I will do is I will just take a special case, because as I said, in the kinds of correlation functions we're interested in, we'll have only one psi, and that the purpose of that will be only to soak the zero mode. No etas, okay, and we'll have only that. Huh? So I will just write down the simpler case. So this is given in the Verlinde. Not the same paper, it's a different paper. It's the second paper that they wrote, which is in the physics letters paper. PLB paper in 87. Or actually that was maybe the first, I'm not sure. 87 paper they wrote, where they discuss. In the previous paper, they don't discuss the commuting systems. Here they discuss the commuting beta gamma system. And they've given it's a horrible formula. I mean, in general, if you write down, if you look at the formula, you just want to give up string theory, you know. But if you specialize to this case, where you have just one psi and products of e to the phi, e to the qk phi k, then it's the problem. It's not so complicated. Okay. Let me just put here zk, let's say. Okay. And there's some number here, k going from 1 to some number here. Okay. The formula is, this is 1 divided by theta. Remember, there is a spin structure here, right? So because we started with the three half differential, right? So there's a spin structure associated with the beta gamma system. So that spin structure appearing here. And then here is sum over qk, zk, minus 2 delta. That's that. And then product of E, zk, zl, qk, ql. Okay. So that's the formula. This is quite a simple formula.
I'm probably confused, but shouldn't you have also zero modes for eta and g loops?
This is a bit strange. Yeah, this is very strange. Actually, no. In fact, I mean, if it's generic formula here, there is a n plus 1 and n. Okay. It's completely different to the standard results. Yeah. I mean, as you're saying, what you should have expected is there's one zero mode here, okay, right? And this will have whatever 2g minus g0 modes, g0 modes. Yeah, exactly. So you should have a g0 modes here and one zero mode there, right? But this is not the case at all here. Yeah, and that has also got to do, and they go through this explanation, and there has been a lot of discussion about it. I think this so-called spurious poles. Okay. It is related to somehow the existence of spurious poles. This current is anomalous. I mean, if you write down the current psi eta, there's an anomaly associated with that current. Okay, and yeah, this is very surprising, indeed.
I thought that contour integrals of eta
Contour integrals of?
around each a cycle, right?
No. I mean, this correlation function is perfectly well defined. There's no problem with that. But there's no eta there, eta here. Yeah.
Probably is the sum of the Q's.
Yeah. This must be again. You see that. Yeah. So this tells you that sum over qk must be equal to 2 times g minus 1, right? Yeah. Yeah. That's the thing. Yeah.
Sorry, I'm still confused because so if you just add, suppose you don't know about the beta gamma system, suppose so you just want to deal with xi eta system.
Yes.
Because you like it.
Yeah.
Okay, then you know that
Yeah. Yeah.
and so then you have to insert these economies of
Yeah, but it's not. I mean, it's a bit peculiar. So so they're really what they're doing is not. They're not really using. They actually get the answer in the beta gamma system directly. Okay. So beta gamma system is very complicated because so beta gamma are commuting systems, right? So when you have 0 modes of beta, it's not that you insert beta. You should insert delta function, right? And then this delta function, they do a Fourier expansion, okay, and then resum all that Fourier expansion, and then they get some answer, okay. Then they say, okay, let's go back to this system, the Friedan-Martinek-Schenker, because this is more convenient for in the standard calculation, right? And they just take the result from the beta gamma calculation and they translate it here. This is the way they're doing it. So not directly starting from the beginning, as you say, beta take eta system, it's a separate free system, right? Then the phi system. No, it's not. They don't do that way.
So, I mean, in a sense, in that sort of bosonization formula, you should forget about the 0 modes of eta.
Somehow, yeah, but yeah. No, I mean, I didn't write the general formula. If you look at it, I mean, maybe I just write down the general formula to show you. I mean, it's not like anything that you imagine for the eta zeta system. The general formula for that amplitude, the top line, is no. So that is n plus 1, right? So that goes like this: j equal to 1 to n, theta of delta minus yi plus x yi, so product over j, I think. This is yj, summed over x minus sum over y plus sum over qz minus 2 delta. See, so this is now many theta functions appearing in the numerator, right? As many as n, the numerator. The denominator is also, actually, yeah, again, a lot of theta functions. There are n plus 1 theta functions here. And then here, okay, there are some, I mean, it's not very illuminating to write down this formulae. Okay, that's that. Apart from, of course, then you have products of various prime forms, etc. So lots of prime forms here, and the sigmas and so on. Okay, but now look at these theta functions here. It's nothing like taking a zeta eta system and 1-0 system and write down the partition functions for that, or correlation functions for that. Yeah, in fact, I don't know how you would start from purely eta zeta. Take it seriously that this is my bosonized picture, right? If I start from there, I wouldn't get this formula at all, right? Yeah.
It's possible that maybe the 0 modes of beta are regularized from divergences that comes from the phi. I mean, there will be some integrals of the integral phi will diverge, some integral of fermionic at 0, and some they combine. In first period, this happens. This is why.
I don't know. Yeah.
You can violate the saturation of 0 modes because of that, because you have an integration of fermions involved and the integration of
maybe I mean, one has to see how, how exactly it works out. I mean, we have to start from beta gamma system and see how it works. I mean, if you just take this,
I mean, starting with that system, forgetting about beta gamma.
no, but I don't see how I mean, if the system is separate system, the phi is a decoupled system. They don't talk to, phi is a system, a free scalar field with a background charge, okay?
Yeah, so where I'm thinking that maybe the bosonization, the dictionary bosonization for higher loops is not so simple. It's not just to factorize the system.
Maybe, yeah,
It's done
maybe.
with the regulator that regularize the integrals of
Could be, yeah.
to get the right answer.
I mean, it's hard. Yeah, okay, maybe. I mean, surely there is some subtlety going on, but I don't know what is that. So you're saying that they're not. You shouldn't think of it as free systems. I mean, zeta, not. Yeah, yeah, maybe.
In Spurious, for example, we got the lambdas and thetas that they behave as the coupled system, but the thetas regularize the integrals of lambdas. So because
Could be.
in
Yeah.
Spurious, you have 11 zero volts for lambda and 16 zero volts for theta, but somehow we get just saturation of 3 lambdas and 5 thetas.
Yeah, but the theories are decoupled, right? The Spurious sector and the theta sector, they don't talk to each other.
They don't talk to each other, so we have, they don't talk to each other in reaction, but if you write the path integral rigorously, no minimal formulas in the regulator of
Yeah, you have this N that...
there's the R theta and R become the bars.
It could be. I mean, maybe that is what. I mean, so what they're doing is they take the beta gamma system seriously. You go through that, right? Now, beta you are expressing in terms of this eta psi and phi. So maybe that is not completely correct, as you're saying. But even you can write it, but then they are not decoupled systems. Somehow there is some coupling. Yeah. But it's. Sorry, repeat again. Yeah. Maybe that is a problem. Maybe, yeah. Yeah. Could be, yeah. Right. Maybe that. Could be.
Is this a mathematical expression which factorize, so you cannot really...
Yeah. This is a horror. I mean,
It's not obvious, but it could be with some miraculous relation which make it factorizing.
yeah.
If you take the equation of between thetas at one loop for symmetry, they are not obvious at all.
Yeah.
On this object, you cannot
Yeah.
really guess.
Right. Yeah. You cannot guess it at all.
There is a different expression which is factorized.
Yeah. I mean, indeed, here you see there is no. I mean, if this is coming from instanton sector, I mean, it shouldn't have the information about the x and y, right? Should have only information about the z. I mean, the tk is zk. This is fine. Zk is there, but then there's this object. So yeah, it's I don't know how. But I mean, as I said, for us, we just have this that situation. There is only one psi. There is no psi eta system. Apart from the one psi, which just soaks a zero mode. Okay. And then the remaining part, this is like a standard scalar field correlator. I mean, standard. Right. Yeah. It's not completely standard even that, though. I mean, because instantons do not come in the denominator. They just come in the denominator. It is not completely standard. No, the instanton sum will come in the numerator, right? I mean, that will give theta function. But this, yeah, the super ghost is a very mysterious object. Yeah. But as I said, I mean, here we can trust it because they get this result from the beta gamma system, original system. Okay, so that is the final answer. No? Now you're just translating the same thing that you got in beta gamma system to this language. No? So I think one can trust that result. No? Yeah. Okay, maybe I should just stop here then. So these are all the Bostonization formulae. Now what I will do is next time I'll go to the actual problem that we have at hand. No? That is to relate topological string to the physical string. Okay. Yeah.